So yeah, welcome to the Fluids and MHD seminar. So today we've got Edmund Chadwick from the University of Salford. So Edmund did his PhD in Manchester and then has had various postdoctoral positions, also working as a senior researcher at BEE Systems in Filton in Bristol, and has been at the University of Salford since 2000, where he's now a reader in applied mathematics. And we'll be talking today on a new approach to solving the Navier-Stokes equations. So I'll turn off my camera if you'd like to go ahead, Edmund. Thanks.
Okay, thanks, Adrian, and also thanks, Daniel, for trying to arrange this talk. So I've given a similar talk just a couple of weeks ago. It did overrun a bit, so I'm going to try and keep it as tight as possible to keep in the time frame. So what I'm going to talk about is it's a new approach to solving Navier-Stokes equations, although for myself it isn't, because it's involving the boundary integral or boundary element method. I've been using that in fluid dynamics for the whole time I've done fluid dynamics. So when I started as a PhD, that was the approach I used, and I've continued that. So it's essentially a talk really about the boundary integral method approach. Okay, so about myself, well, Adrian's actually just been through all this, so I don't really need to go through that. Apart from now, I'm looking at since I've been at Salford in the maths department, I've been looking at boundary integral, boundary element method for fluids. Okay, so the overview, I'm going to state what the problem is, then give the governing equations, which are the incompressible Navier-Stokes equations. So I'm not looking at compressibility here. And then I'm going to go through the actual boundary integral formulation, the velocity representation that I get, distance and smoothness for the solution, and then a suggestion for experimental verification of the theory. Now, the approach itself, it's what I'm presenting today has in large part already been published in Physics of Fluids, and in two papers. One actually was originally on the Euler flow and Eulerlet, and then a subsequent one on Navier-Stokes flow and Navier-Stokeslets. The Lets means Green's functions at the end, so I've just borrowed the standard way of describing Green's functions, so by putting a lit at the end of it. Okay, so what the problem is I'm looking at or addressing today is I'm looking at some sort of body in a fluid, and essentially an exterior domain. So if we look at the diagram here, the figure 1 whoops. What's happened there? The figure 1 diagram there, we have a body, and over the surface of that body, I'm going to distribute special functions called Green's functions, and that body is parameterized by this by the point xi prime. So xi prime means the parameter values over the body surface, and that ends up as an integral distribution. So it's also the variable of integration that I get in the representation. And xi is a point in the fluid where we want to work out what the velocity and pressure are. So in the Green's integral distribution, the idea is to represent the velocity in this particular case as an integral distribution of Green's functions described over the body surface. Okay, so I'm going to give you the final result that I've got at the moment, and this has been published in Physics of Fluids, and it gives the velocity as an integral distribution of the Green's functions. So I use the tensor notation, U subscript 1, U subscript 2, U subscript 3 for the velocity components in the x1, x2, and x3 direction, or more commonly x, y, z direction. X is three-dimensional space and t is time. The Green's functions themselves are the U subscript ki's. So there are 3 Green's functions themselves. So how you read that U subscript ki that's in the integrand of those 2 integrals there is the k refers to the particular Green's function. So when k is 1, it's a 1 or drag Green's function. When k equals 2, it's a 2 or lift Green's function. When k equals 3, the 3 or side force Green's function. And then the I is the velocity vector component for that particular Green's kth Green's function. Okay, so what we're saying here is the velocity can be represented by an integral distribution of these Green's functions. So in a sense, the velocity has been linearized here because it's represented by that integral distribution. And that goes over a volume V minus VB, where the body itself is within a volume VB and has a surface S bounding it. And I'm looking at an exterior domain, but also I can look at the interior domain. And the interior domain would be exactly the same, except the first integral, instead of it being V minus VB, it will just be integral over VB. In actual fact, to get this representation, I need to look at the exterior the exterior domain and the interior domain together for the same problem. But I'll come to that later. So Fi here is that capital Fi is it'll work out as the stresses or force per unit area. So the integration over the surface of Fi gives you the force on the body. And also very often we look at things from initial value. So the first integral over V minus V by V minus VB is what's happening when t equals 0, because we've got the velocity there as a function of x prime 0. So over the figure 2, that's this volume represented at the base of this figure. It's a bit difficult to read. What's happening is time is in the vertical axis, and then the spatial coordinates are in the horizontal axis. So in the horizontal axis, although it looks like an area, it's actually representing a volume. And then as you go vertically upwards, time changes. So we can see that the body may occupy a volume, VB at time t equals 0. And then at subsequent time, the body moves. So for example, here, the body is kind of wobbling about a bit. And so therefore it's traced out this peculiar cylindrical path. And that then gives over time the space-time body surface tracked over time. So what's represented here in figure 2 is a kind of space-time diagram. And this is the surface, this is the domain, boundary of the domain that the boundary integral representation uses. So what the boundary integral representation does is it represents the velocity as a distribution over the boundary, and there the boundaries are listed with kind of within that figure. Okay, so now the governing equations themselves. The first one is, well, the equation itself, the primary equation that we're trying to solve is the incompressible Navier-Stokes equations. So it's given by equation 2 here, and it's quite condensed notation. So it's the notation kind of taken and adapted from general relativity. So I think what I'll do is I'll just escape from here and go to my overhead camera just to describe more what's going on there. So let's have a look. If I stop that share. And share screen. Okay, so this is now going to my overhead camera on my desk. Okay, so what I want to do is I'm going to look at okay, so it's these equations here, and I'll just briefly describe what these mean. So for example, ui semicolon I there, I can just write that out. So that's ui semicolon I, that's shorthand for dui by dxi prime. So where we have a prime here, it just means, where we have a semicolon here, it means a differential with respect to x prime. And if we have a repeated index, so here you've got I and I repeated, that means using the Einstein convention, that's du1 by dx1 prime plus du2 by dx2 prime plus du3 by dx3 prime. So that's what this notation means here. Okay, so that's for this one. So that's from the continuity equation. So the Navier-Stokes equations are paired. We've got the continuity equation, and then this is the force equation. So all these are the forces per unit volume that are going on in the fluid. Okay, so these first two are because of the velocity of the fluid, the change in momentum as the fluid moves. So the first one is an acceleration. There's no, what I've done here is, strictly speaking, there should be a row in front of these, of course, for density, because if it's force per unit volume, but I've divided by rho, and I've absorbed it into the pressure here. Okay, so that's a technique often employed for when you're using incompressible Navier-Stokes equations. So the P here actually isn't pressure, it's actually pressure per unit density. So then we've got an acceleration term here, and then the inertia term due to the fluid moving, and then a force term per unit volume due to pressure, and then a viscous force term. And they're all balanced from Newton's second law. Okay, and then just to notice as well, in the notation I'm using, if I've got a little I or a little j or a little k, it means the spatial index is going from 1 to 3. If you've got capital I, it means it goes from 0 to 3, so that's space-time. When I equals 0, that means the time index. So this ui semicolon 0, for example, ui semicolon 0, that means dui by dt prime, essentially. Okay, so that's the incompressible Navier-Stokes equation. Of course, they're notoriously difficult to solve because of this nonlinear term. And of course, when you have a nonlinearity in the differential equation, that's the problem where you cannot solve things. So just to go through briefly why that is the case, I'll just look at some basic examples. So for example, the simplest linear differential equation you could think of, say, is phi by dx equals 0. So if you looked at solutions of those, phi a by dx equals 0 and phi b by dx equals 0, then you can generate a second solution, which is d by dx of phi a plus phi b equals 0. So when you have a linear differential equation, you're able to generate extra solutions by a linear superposition of solutions you already have. And so finding a general solution is quite straightforward. And of course, that doesn't happen for a nonlinear equation. So if you have d phi squared by dx equals 0, you can see the same thing doesn't happen, because you then have this one and this one. But then when you looked at d by dx of phi a plus phi b all squared, that's in phi a squared plus 2 phi a phi b plus phi b squared. And although they be 0, so d by dx of all those, although they are 0 because of this condition, that one necessarily isn't. So you can't build a superposition of solutions. And if you have a solution to a nonlinear differential equation, it's only usually specific to the particular example or problem you're looking at. So if I'm saying for this solution of the Navier-Stokes equation, I have this representation, which is essentially a linear superposition of the Navier-Stokeslets. Can I do that, or it doesn't seem to quite be obvious, or that might be the case. So, although having said that, you can see from the Navier-Stokes equations, they're kind of, there is a linearity in the velocity from the continuity equation. So there is a superposition of solutions from the continuity equation, although obviously it isn't for this one because of this quadratic term in here. But having said that, if we look at, we can see that you can get representations where you get a linearization in the velocity. So the most obvious one is for Euler potential flow. So if, for example, I have ui equals phi semicolon I, so the velocity u can be represented by potential phi, the derivatives of it. Then if I put that into here, then I get phi semicolon I0 plus phi semicolon j, phi semicolon ij plus p semicolon I. And for the Euler equation, the Euler flow assumes that mu equals 0. So there's no viscous term equals 0. And then phi semicolon I equals 0. And then, of course, you can see that you can give an outer differential to this one, because this one can be represented as a half phi semicolon j, phi semicolon j, semicolon I. So when you differentiate through that, you see you get that term. And then this one, of course, is the same as phi semicolon 0i. So there's a differential respect to y in the outer one of all those. So integrating through, I then get phi semicolon 0 plus a half phi semicolon j, phi semicolon j plus p semicolon I equals 0, which is essentially Bernoulli's equation. So because the rho has been absorbed in there, that's like a half rho u squared term. That's the kind of the kinetic energy of the Bernoulli equation. I didn't include the rho gz, but if I went through the force per unit volume with the body force for gravity in there, I'd have the rho gz term in there as well. And then, of course, you can see, well, you can solve the velocity by a linear equation for Laplace, and then once you've found that, then you can substitute in here, so there's no, and then work out what P is. So then P equals minus that one. So that's a kind of standard way of solving problems for Euler potential flow problems. You first of all solve the problem for the Laplacian and the potential, and then work out what the pressure is once you solve that, because then you know these two terms. And so the nonlinearity somehow has kind of got absorbed into this relation relating the pressure, but the velocity itself is linear. So you can see that does happen in particular very specific cases, but can it happen for this case? So that's what we're kind of looking at. So this is the Navier-Stokes equation now, and of course then you've got a similar equation for the Navier-Stokeslets. So here with the Green's functions, what you do is you say, instead of the right-hand side equaling 0, it equals the Dirac delta function response. So this is a direct delta function over the 4 space-time coordinates. So there's 3 space coordinates and the 1 time coordinate. So that actually means here minus delta of x0 minus x0 prime times delta of x1 minus x1 prime, delta of x2 minus x2 prime, and delta of x3 minus x3 prime. And when you integrate across the Dirac delta function of any one of those, it gives 1. So the definition of Dirac delta function is the integration minus infinity to infinity delta of x dx equals 1, and it spikes, so delta x also equals 0 when mod x is greater than 0, and then it spikes up to infinity, or spikes up when x equals 0, such that when you integrate across, that holds. So that's the Dirac delta function. So what this means then is this equation is force per unit volume, and then these are we've got 4 Dirac delta functions integrated across, and they pick out the kth Navier-Stokes in each case. Now, originally I said that when I have a I semicolon I, Einstein's summation, you sum over those over the i's. If it's a little I, that's just space. It goes from 1 to 3. But here, this Navier-Stokes equation is for the k different Navier-Stokeslets. So k equals 1 being the drag Navier-Stokeslet, k equals 2 the lift, and so on. So here the k isn't summed over because the k refers to what particular Navier-Stokeslet it is. So we've got to be careful. So for example, with this equation, this term here, that k and that k refer to a particular Navier-Stokeslet, and it isn't summed over, whereas that j and that j are summed over. That's the Navier-Stokeslet that's used, and the solution and the equations for it. So the ith velocity component of the case Navier-Stokeslet, and the functions themselves are functions of x minus x prime. So it's as if we've got a Green's function positioned at x prime, giving an influence of the function itself at the position x away from x prime. And then here we've got a comma differential, so that should be comma there, not colon. Comma differential, which means it's differentiated with respect to the x value, not the prime value. So that's the variable in the fluid rather than the variable that parameterizes the boundary. And then this delta ki here is the Kronecker delta term. Okay, so have I gone through everything that I want to here? I think so. So now I think I'll just go back to the actual slides themselves. Okay, so that's where we're up to. What I'm going to do now is look at the Navier-Stokeslet asymptotically, so close to it, close to the origin of the Navier-Stokeslet and far away from it. And so from dimensional analysis, if we look at the velocity size u time t, distance away from the origin L, then we see the time-dependent term of in the Navier-Stokes equations. That was the ui or uki comma 0. So that's a differential of the velocity with respect to time. Has a dimensions ut to -1, and then the Dirac, on the right hand side, the Dirac delta function, the 4 components of it, 3 space and 1 of time, give that as a dimension. And then from those, I know that in order to get a solution that is meaningful, it must be that the time-dependent term and the flux term are balanced, because if they weren't, if all the other terms are differentials with respect to spatial vector, that will mean if that term wasn't included, the final solution will have in it a factor which is the Dirac delta function in time. So that's kind of a solution that only exists at a specific time, and then no further subsequent time. So in order for the solution to have any meaningful solution, it must be that these two terms balance each other. And that means then the velocity must go as L to the -3. And so then the inertia term must go as L to the -7. Oops. And then the viscous term, the UKI comma JJ, goes as L to the -5. So as L tends to 0, we can see that the viscous term is much smaller than the inertia term and disappears. So if that's true, then we're approaching an Euler flow representation because the viscosity is becoming negligible. And so asymptotically, we get the Eulerlet, the Navier-Stokes tensor Eulerlet near the origin. And we have a solution for the Eulerlet that's already been published. And this briefly goes through how you can work that out. If you go back to the Navier-Stokes equations here, this term is going to drop out because asymptotically it disappears because that's a viscous term. And then the pressure I can write as a summation of two pressures, an Euler pressure and a Bernoulli pressure. And then the Euler pressure I can relate with the time dependent term, and the Bernoulli pressure I can relate with the inertia term, which will become basically the inertia term in the Bernoulli equation itself. So I've got this split here, and then in order to solve the problem, one is related to the Kronecker delta. So equation 5 is related to the delta function, the Kronecker delta term, and then equation 4 must balance exactly, which it will do if PB is the Bernoulli pressure. Okay, so how we solve that? So looking at equation 5, we can differentiate through again. So if we differentiate through again with respect to I, from the continuity equation, that UKI e comma 0 term will disappear. And so we get PKE comma II equals minus delta comma K there. And then letting one of those delta functions is a delta function in time, so I can take that out as a factor, and then that gives me the Laplacian source for this pressure P star, which is taking the opposite sign of it is 1 over 4 pi r. And so from that I can work out the Euler pressure, and then from that, substituting back in, work out the Euler velocity, which is given by equation 8. And then putting all those back in, I can work out then what the Bernoulli pressure is. Okay, so I worked out what's happening asymptotically with the Navier-Stokes as it tends to the Eulerlet near, and the near field asymptotic. The far field asymptotic, as the velocity decays to 0, it goes to the Stokeslet because the inertia term disappears because it's got a quadratic in the velocity. And the solution for that is well known. You can get it from Fourier transform analysis, and then that gives us a solution for the Stokes velocity and Stokes pressure, the Stokeslet, which the Navier-Stokeslet tends to in the far field. Okay, so now that we've been armed with these, we can now actually look at the boundary integral representation itself and giving it for the velocity. So equation 13 here, that equation is the starting point in Oseen. So when Oseen looks at the boundary integral method, this is his starting point. He gives an integral over the domain of Fi times by U, which is the Fi represents the Navier-Stokes equation for the fluid point, UKI, which is the Navier-Stokes velocity, and then FKI, which is the Navier-Stokes equation for the Navier-Stokes times by UI, which is a fluid velocity. And he takes those away, and because Fi and FKI are identically 0, then this will be 0 as the main. That's excluding, of course, the point here where the Navier-Stokes is, because where the Navier-Stokes is, you get a Dirac delta function response, so it won't be 0. But excluding it means you can, doing it in this way by putting a little boundary around the fluid point. And then if we look again at the space-time diag figure, so from figure 3, so the point xi we've excluded from the domain sigma by putting a small boundary around it, and we have a boundary when at a particular time at minus x here, and then another boundary for the body itself. And we can consider the domain consisting of 2 parts, the domain exterior and the domain interior as well. And it's important to use both of them together because they certain terms cancel each other out in the analysis later on. Okay, so that's my domain. My domain, actually, the sigma domain, is a domain bounded by all the boundaries you can see in there. And then what we do is we position this Navier-Stokeslet at the point xi. It's actually not, strictly speaking, a Navier-Stokeslet. It's kind of the sister of the Navier-Stokeslet, because Navier-Stokes itself is a function of x minus xi, whereas here we're going to, if we position Navier-Stokeslet there, it's a function of xi, so a function of xi prime minus x rather than xi minus xi prime. We position that sister Navier-Stokeslet there. What that means is in the Navier-Stokes equation here, this differential is differential with respect to x. So x prime is considered to be the point where the Navier-Stokes is, and x is considered to be the variable. Whereas if I consider x prime minus x, it's the other way around, and the x prime becomes a variable. So to change from one to the other, because it's a simple x minus x prime function, we'll change the sign when there's a derivative to becoming negative. So the sister Navier-Stokes equation will be a negative there because it's one derivative, a negative there, a negative there. There's 2 derivatives here, so that actually won't change sign because it'll change sign twice. So in total, it won't change its sign. So that's what's positioned there, which is kind of like the key or core of boundary integral methods. But then at the very end of the analysis, we can then say, okay, although we positioned the Green's function there, it can equally be seen as a function of not of xi prime minus xi, but as a function of xi minus xi prime. And then we get the distribution of Green's functions positioned over the various boundaries influencing the point xi. Okay, it's the equivalent thing. Okay, so now I'm going to look at the integrand and start to change it, because I should really just go back. I think what I'm going to do is go back to my overhead video. Okay, so the Austrian representation has got some sort of integrand, d psi equaling 0. But of course, for the boundary integral and boundary element method, we want the boundary of this domain, not the domain itself. So we have this as a domain. We want to look at the boundary of the domain. And for this, we can apply the divergence theorem. So we know the divergence theorem that the integration over the domain du, if I look at the parameterized by the prime boundary, dui by dxi prime, or if it's I can call it the whole of the space-time boundary like that, equals integration over the boundary of ui prime ni, and that's differentiated over the boundary, that boundary there. So what's happened here is with the divergence theorem, you've got a divergence of a vector, and that equals the flux out across the whole of the domain, and that equals the flux out across over the boundary. And so essentially what's happening here is, and of course you can consider, for example, ui equals a, say delta I1 or delta I0 or something like that. Just look at one component and get a value, and you can see that the same thing happens, that essentially the differential over the domain changes when you look at the boundary of that domain, it changes into a normal. So essentially in the divergence theorem, what we're looking for to get our domain integral into a boundary integral is some d by dx I or I prime of something, whatever it is, and it can be anything, in this form. So we want the integrand to have a differential on the outside. And then once we've got the differential on the outside, that means we can replace it by the boundary of the domain of whatever this is, times by ni prime over the boundary. Okay, so that's the kind of crucial element of particular the boundary integral representation method that Oseen uses. That what he's wanting to do is express the integrand in such a way to get a differential on the outside. Then he can apply the divergence theorem to get it as an integration over the boundary, where that's a normal ni. So okay, so this integrand here, it wants to be reformulated to get a differential on the outside, which is basically in this primed coordinate, a semicolon I on the outside. So then we look to manipulate this integrand to do that. Okay, so we can get some differentials on the outside here, so they're okay. But then there's a part qk where we can't. Some parts of it we can. So some parts of qk, there's this part qk j star, which is this one. So that we can, but this part, the other part we can't. So we need to rewrite it. So the whole idea of the approach to try and get a differential on the outside when you've got a nonlinear part to it is to introduce a potential form here. So potential for the nonlinear bit. And then if I can get it in that form, then everything on the integrand is differentiated on the outside, and then I can change the domain integral into a boundary integral. So that's the idea, and the question is, well, can we do that? And then what's the properties of that? Will it be amenable to the standard analysis in the boundary integral method? Okay, so I'm going to write that in this form. So I'm going to say that this, essentially it's a divergence for each kth part, because J semicolon J is the divergence. I'm going to write it as a vector in the unit vector capital R direction, where R is in spherical polars here. Okay, so what that means is we've got, just put that up here. We've got essentially something like AJ semicolon J here. So if we're looking at, so that's a divergence, but if we're looking at it for some orthonormal coordinates, so for example spherical, so you've got R, theta, and alpha, so spherical polars, then you're going to, then you're saying your vector A is being represented by AR in the unit vector R direction plus A theta in the unit vector theta direction plus A alpha in the unit vector alpha direction. And then in order to work out what the divergence of that is, we need the lengths associated with them. So we need HR, because that's already a radius is already a length. HR is going to be 1. A theta is the length R, and A alpha is the length R sine theta. Okay, you see that's from where you have some point R subtended by an angle theta. It's coming around by an angle alpha here. The length change in this direction is 1, so HR is 1 because R is already a length. Here, as you're coming around, it's R d theta. So the H, sorry, that's HA, H and H there. The H theta is R. Then here R sine theta d alpha, so H alpha is R sine theta. So when I put that in, I'm going to get, for orthonormal coordinates, is 1 over H R H theta H alpha times by dr of H theta H alpha AR plus others, the A theta and the A alpha. But because I'm saying it's just a component in the unit vector R direction, I'm saying they're 0, so I've only got that one. So I've just got this one here. And so putting in for HR, H theta and H alpha there, that then becomes 1 over R squared sine theta d by dr of R squared sine theta AR. And then the sine thetas, because it's differential with respect to R, as R changes, theta's orthonormal, so that can be brought out, so they just disappear. Okay, so that gives this here, and then I can then integrate that up then to represent this as a potential. So that's the idea. So I'll go back to the notes. Okay, so I've got to this point here, I've introduced a potential, and then this is what the form of it is. Then integrating up, I can get what the value is, and then that integration now goes from infinity to the point R. So here, if you look at figure 4, if I've got a point xi and a point xi prime, I've got this part of this new function, potential function, is obtained from integration going from infinity to r, where r star now is this integration, variable integration for that integral. Okay, so that's a key point or part of this new method in order to get a boundary integral representation in this way. So then once I've used that, you can then see, okay, now I can represent, change the boundary integral, put a differential on the outside, so the domain integral, put a differential on the outside, and I get a boundary integral. Okay, so that's the approach, and then I work out what this boundary integral is across all the different boundaries that I had. So I'm working that boundary integral now across this small bit close to the point, this bit far away from the point, and then over the boundary, the body itself, and also over the initial time, if there is an initial time. Okay, so I work it out over all those three different boundaries. So that's the integral contribution over the boundary around the point. And then I've got to work out these bits. Okay, so now this is a whole load of tedious calculation, which I'll just skip through. So it works out the first two terms give the contribution u minus uk, the third is 0 and the fourth is 0, and then this one has in it this potential. It's got to split up into 3 bits, and then each of those 3 bits has to be worked out separately. And then when you do that, it all gives 0. So the integration around delta is minus uk. And then for the integration around the big boundary, okay, so that's this one here, the Navier-Stokes tends to Stokeslet. So this is why I needed to work out the asymptotics, because to do it, I needed to know that Navier-Stokes there tended to Eulerlet to use it, and Navier-Stokes tends to Stokeslet for this large boundary. And then putting that in, it works out that that contribution is 0. Okay, so the only contribution I get is from the body boundary itself. Okay, so then I look at it from the external domain and the internal domain. So this is for the external flow problem. I then get this representation for the velocity. And of course, you can see there's quadratic terms there in the integrand itself. But I can also do, for exactly the same problem, the internal domains. So what I'm doing now is I'm assuming that there's fluid flow inside this surface here. The conditions are given by the body boundary surface around S. So so then I'm looking at an interior domain problem as well as an exterior for exactly the same body surface evolving. And then that gives me this for the external and this for the internal. And then I can see, because the velocities are continuous in both the fluid velocity and also the Navier-Stokes velocity continuous, then the FKij is the same internally and externally, and so is the QKj, but the stresses won't be. So that plus is for the external domain stress, and that minus is for the internal domain stress. And then in this way, combining them together, adding them together, I just get the velocity in terms of the stresses with the linear component of the Navier-Stokes velocities. Okay, and then I can do a similar thing if I've just got an initial value problem now, so no body at all, but the velocity has been stipulated at time t equals 0. The outpointing normal then is just in the time direction, so I just get the time component, which is that one. So it's also represented by an integral distribution of Navier-Stokes. And then bringing those together then gives us my final result, the result that I wanted to prove. Okay, so now I've got to the actual result that I've proven, and I can look at some properties of the solution. So first, I can look at existence and smoothness. So I know for this problem, in the far field, it must decay like the Stokeslet. So that must be a condition of the problem for a solution to exist. And also the derivatives must obey the Stokeslet derivatives as well. So I can work out what properties it must, how it must decay. And then I also know that the energy is bounded because it's in the far field, it's given as the Stokeslet velocity. And I can also show that the velocity itself is smooth for the initial value problem without a body there. And so what I can do is, at x equals 0 at the initial time, I've been given what the velocity is, so the velocity exists. And I also know from the representation, it's at integral distribution. And so that integral distribution must exist as well. And then I can deform that. So I can form that integral distribution over initial time to 1 over a far field boundary through the boundary integral method. And then I can see that over the far field boundary, the Navier-Stokes become Stokeslets, 10 Stokeslets. So therefore the velocity must be smooth. And also because I know the velocity exists at initial time, because I know the velocity exists at initial time, I know that these Fi components here must be reasonable in the sense that they must give a solution. And then at a time t later, I see that it's exactly the same representation, because at a time t later, there's no contribution to the boundary. So boundary here, if it's a time t, it's say up here. There's no contribution from the far field boundary because the energy is bounded. So it's given by exactly the same representation, which I've shown exists as smooth. So at time t later, the velocity must be smooth as well. And if I wanted as well at a time t later, that far field boundary I can represent by a near field boundary around the point. So therefore, the Navier-Stokes approximate to Eulerlets, which also for r bigger than 0 are smooth, and so the velocity must be smooth. And I can do a similar thing for the Navier-Stokes velocity. So I know the Navier-Stokes velocity close to its origin is behaves like the Eulerlet, so I can represent it as a boundary Eulerlet distribution. And then that is represented by an integration. Then again, I can deform it again as a far field boundary. And then because I've deformed it as a far field boundary, the same analysis I did for the Navier-Stokes velocity applies. So the Navier-Stokes velocity must also be smooth. And then I can work out that the pressure is smooth by, so this is quite well known, so applying the Helmholtz decomposition. So any vector can be represented by a divergence-free component, which is that one, and also a curl-free component, which is this one. So decomposing in that way, I've written hi here, which is called a head function, which is the inertia term. Decomposing that in a divergence-free and a curl-free components, I can substitute them in, and then in a similar way that I did for the Euler flow potential representation at the start of the talk, I can get an expression for the pressure, and then that then gives me, because I can work out phi and h explicitly in terms of the velocities. If the velocities are smooth, phi and h are smooth, and therefore the pressure must be smooth. Okay, so the final thing is just, can we verify this? So what would be an experimental verification of this? Well, one would be looking at what's called a space-time ball. So if we have a sphere, which is initially like a spherical balloon, which is initially completely deflated, so it's at a point, then we blow the balloon up, inflate it, and then at some, so here in our space-time diagram where x0 is time is vertical, so at the very bottom, This is where we start inflating the balloon to where it crosses the xj axis, and then we start to deflate it again in such a way that in space-time it gives you this space-time ball. Then we can position a hot wire probe and work out what the velocity is and the velocity change. And then from the boundary, the resulting boundary element method that we get for the velocity, we can get a velocity numerically, and then we can see if they're the same. So that's one way of verifying the representation. So what we do is we'd use this is a traverse mechanism which we can use to very precisely inflate and deflate the balloon, the spherical balloon, in a wind tunnel. We wouldn't use that one, we'd use one of the big ones. And so essentially we'd have the hot wire here. So this diagram isn't really representing the right thing, but I just put it just to give an indication. Instead of a pitot tube, we'd have a hot wire there. This would be the balloon inflating and deflating. And we'd have a much bigger chamber. We've got lots of different wind tunnels at Salford. We'd use one of the bigger ones, and we just put it in one of those big chambers so the walls didn't influence anything. And then work out what the velocity reading was over time and see whether it matched it numerically. Okay, so I have overrun. I've stopped there.